Welcome to the final talk of Kicon. I'm super excited to be giving this presentation. You're going to see two things in this talk. For one, I'm going to talk a little bit about my master thesis, which the concept that I'm going to present to you stems from. And then I'm giving you a slightly random set of Git information that you may or may not know that might help you improve workflows of variant management in Git. I would love to discuss your ideas on that either after the talk or at our after party when you, because I'm looking forward to improving that tool. But let's come back to the talk. Storing more information about Git. You probably already know Git is awesome, and I know that at least since I finished my master thesis. Question is, did you know how awesome it is? And I tried to convey this information to you. So let's jump a couple of months back when I wanted to do my master thesis in applied computer science. I was looking for a very interesting topic, something that would have some real-world use case. So I ended up at the chair for software engineering because I wanted to improve software development. I love to write code. I'm not too much into hardware, but my colleagues Odin and Stefan do the more of it. So yeah, what did I want to improve about software development? Most of you might have written code, and you probably know that to actually do industry-grade software development, it's not about making it only work once and on your machine. It's about working in teams. It's about setting up systems that allow us to have quality assurance, that allow us to reason about our code, to plan, to have people like product managers. We have customers that do not know how we implement code. We need to confer with them, and software development is wild, as is hardware development. There are tons of ideas how we can improve that, and the one that I focused on was feature-oriented software development. This is a concept where I have code that is structured in features, and these features are composed to different variants of the software. The concept of software product lines is typically used in automotive industries or in robotics, and it's only one of the many software engineering techniques where features might play a role. We have the terms of feature models, which describe which features go well together, which are exclusive. So when we write code, we need to think about which features might be in our context. If we, for example, need to have a Bluetooth driver and think about it influencing our runtime, or if we know that we're on a system that allows us to store files or whatever. Variant management describes having these different products and evolving them, hopefully, simultaneously. So if I have a customer that has a bug and I fix that bug, I probably want to fix that bug in all other products as well. Which products do I want to fix bugs in? That's not easy to reason about. And the question, what are the features, is popping up quite often in these setups. Now you might ask, well, this is a hardware conference, why are you talking about software development? Well, something that I recognized throughout the past year is the ideas of version and variant management do apply not only to software management, but also to hardware management. We all know that KiCad exists. You probably all use Git or some version control system to version your files in within KiCad. And many of you might have already worked on hardware products that are not only existent in one variant, but that are slightly different. I mean, think about just using different capacitors because you just chose to have another one because one is not in stock anymore, and have an entirely new product that is a different version in your version control system, but still somehow related to another variant. The questions are the same. Which variants exist? How do they differ? What is similar? And how can I evolve them? So what's the goal of this talk? I, of course, want to present to you some lesser-known Git features. I hope they are lesser known. I want to show you how you can add meta information to your Git. Because as you might have read in the abstract of this talk, our commits exist in a broad concept of product. We usually know what we're doing when we're committing. That is not necessarily true a month afterwards. I probably guess you have already looked at some commit and were like, I am the author of this. What was I thinking? So I want to discuss possibilities and also limitations of different approaches on how we can add disinformation within Git, because I think that having better tools within development needs to us to better collaboration and also in general better development. So yeah, back to my thesis. What did I do? I'm presenting to you the methodical approach very briefly. First of all, I wanted to understand Git and feature-oriented software development problems, because only by actually characterizing the problems I can come up with a solution, right? So what exactly do developers do? Which workflows would they like to do, but they can't because the tools are not representing these ideas? I wanted to know, how does Git store information? I mean, we all know about commits, right? But what does it actually mean that information is stored within Git, and how can I build upon this concept? And which Git extensions can I actually implement that help developers and are implementable? Because I can think of a lot of things, but if they become too complex to even create a prototype, that stuff will never ever make it into the industry, right? I also wanted to evaluate the actual usability of my tool within a user study. You will get the link. I will show you some QR codes if you're, which you can scan if you're interested. I'm not going to present a ton of the commands, but you can test them out yourself if you want to. Let's get to understanding Git. Who of you has ever looked into the fundamentals of Git, like how it actually is programmed? Oh, quite a few. That's going to be exciting. Call me out if I make any mistakes, please. Git has a design philosophy. Linus Torvalds came up with Git when around the year of 2001, when Bitbucket wasn't meeting the requirements they had for developing the Linux kernel. So he gave a lot of he had a lot of email correspondence with his fellow developers about what to do about the problem of version control. And he wrote some emails about what Git actually was. He took, I think, a couple of days in some hut somewhere in Scandinavia and implemented Git within 4 days. He described Git just as a file system. It's a distributed file system that allows you to share content. And if you wanted to do, you can make a version control system on top of this versioned file system. But Git, in its essence, is a distributed file system, and thinking about that helped me a ton, because whatever I want to put into the file system, I can version within Git and share with developers. How exactly does that work? Git has an object model, and each object has a char. This value is calculated from the content of the object. So if two objects have the same char, they're equivalent. This is an important concept that they're using thoroughly. But let's go back a little bit. Everything in Git is an object. You might have already looked in the .git folder that occurs once you do git init. That's where all these Git objects are stored. So something in Git can be a blob. That's a representation of a file. It has contents and it has a name. Now, oh, do you actually see my mouse? Oh, you don't. Can I fix this? I am not too sure. So yeah, we have the blob, which is our most basic file representation. And then we have trees that consist of multiple files that make up the tree or folders. And when we do a commit, that is a snapshot of a file tree. This commit references the tree, and in the tree we have the chars of the files, and then we can reference the files. So it's like a lot of pointers going on. A commit is an object that references, as I said, the trees. It also has a message and an author and a timestamp, which means that the char of the commit uniquely represents its content, and you cannot create a new commit with the same char if it's not done by the exact same person at the exact same point in time. That's why Git can pretty clearly tell you if two commits are the same or not. If we work with tags, which you might have heard of as well, who of you has heard of tags? Most of you, I guess. Oh, not everybody, actually. Okay. So a tag in Git is like a named pointer to a commit. It's literally a name and the SHA of a commit that it points to. So yeah, this is the Git object model. What's important? I'll just recapitulate that again. We have the SHA that is calculated from its content, and then we have like a recursive structure of I have an object that references different objects of SHAs, which are the pointers to the files that I can recursively look up. How does that look like? This is what the object store in Git looks like. I have put on a QR code from the GitHub blog, which is a very nice series about the internals of Git. If you like to read blogs, I highly recommend this one. And as you can see, these are the object IDs, the SHAs, these very long strings nobody really can do anything with. They're either commits or blob or whatever. And then we have the reference store, which is what most of us as developers work with. Main is, for example, a branch name. It's the head of a branch. So whenever I have a branch, I point to a certain object, commit usually. And when I add a new commit to my branch history, what's internally done is that the pointer of the head of the branch points to the new commit. Something that I never knew before, and I found that very interesting, and it helps a ton to understand why Git sometimes has merge conflicts or unresolvable history, because if somebody pushed something on the remote, it has a different commit hash on the current head than you have on your local development. And because these commits have nothing in common, Git doesn't really know what to do. And then these weird merge conflicts occur, which you might have or have not experienced. So yeah, why does it not go forward? Oh yeah. So how does Git create a commit? Like the most basic block of version control systems. A commit is a referenceable snapshot of the file system, which means whenever you look at the contents of the commit object, you can always restore what the file system looked like at that point in time. There's no need for you to understand the history prior to that. You just need that commit. So it's a referenceable snapshot of the file system that's different to other version control systems that just do deltas. How does Git actually create a commit? First of all, we need to create that blob, the snapshot, the content of the file system. So each file is created as a blob, and then we structure them in the tree, which is a folder-like structure with all the SHAs. And then we can decide to actually create a commit by adding a message, setting us as authors and as a timestamp. At the end, when the new commit object is created, we update the pointers, as I already explained. And there we go. We just committed something. Git has a concept of plumbing and porcelain. I'm going to explain that to you because I found that very helpful throughout the development of my tool. It's not about making the perfect command in the very beginning. It's about thinking of atomic steps that I need to do to add information, and then combining many of these atomic steps to actually make a nice command. So plumbing would be the kind of ugly, hard-to-use commands that you would need to look up constantly. Porcelain commands are the ones that we usually use on a daily basis. So we have a toolkit for a distributed file system, which is super nice because tons of information can be stored in the file system. And we also know that Git is meant to be extended by design. Because Git was built to not be complete, this invites us to build multiple concepts on top of this file system, which is also something that I'd like to discuss down the road with you, because whatever you can think of that's storable in a file system, we can share with Git. Okay, context switch. We now talked a little bit about Git, and now we want to look at feature-oriented software development. we have the problem of, well, this 2D problem of variation and version control, which all of you know that already had variants in their hardware, right? We have multiple variants of the same product at the same point in time, and then we do a new commit, which is a new evolution, and somehow all these variants still exist with this new evolution. Some of them have not changed, some of them have. So we have like two axes of the problem that are kind of hard to manage, because technically speaking, whenever we do a new commit in the version control space, we would also want to do changes in all of the variants of our product, because they might need to change as well, because we might have just fixed a bug, selected a new part, added crucial information, whatever. Internally, that means I need to figure out which variants are touched. And I might also need to figure out, if I work on some variant of the system, which features am I actually touching? Like, do I know what is given or not given in my variant? For hardware, that might not be as hard as it is in software, where people do weird if-dev definitions saying, if this feature is available, this code is relevant, and you're like, I don't even know if that feature is enabled for the use case that I'm implementing. So yeah, these are hardships of feature-oriented software development, and I'm most likely not going to solve them all. What am I going to solve? I want to help understand the code base in terms of features, which means I want to understand which features are actually present, because if I know the features, then I know what I actually want to look for. I want to research information about a feature. That might involve the files that a certain feature touches. That might involve the commits that a certain feature touches. That might involve the authors, because sometimes it's nice to know whom to talk to, right? If I want to research a feature, that involves me being able to add these information into the system. That's why I created feature add commands. And the last thing, and the most interesting one, is the check for updates. If I say that I alter the feature, I want to know which branches, a representation for which variants usually, also touch said feature. And then I need to think about workflows for updates. So how do I get there? How do I get these feature information into my Git? Little background information: there are already tools that allow you to store such information, but these are not incorporated within Git. You would need to synchronize these information with another software tool, which was the problem that I ultimately want to overcome with Git. So it's everything, all data in one place kind of approach. The metadata extension concept that I call Git with features is what I'm going to present to you now. It touches the concept of features, but I want you to be open to replace the word feature with bug, variant, vendor, whatever. I never actually delve on the concept of features being some code, just so you can keep that in mind. I think it's a very transferable concept. Back to the object model. The blue one we already touched, and the green ones I added. And there is only one line that connects my system. Oh, you can't see my mouse, right? So there's only one line that connects the blue part of this diagram with the green part. And that's the line from the commit to the commit folder. So I decided that I want to create a file system structure where each feature gets its own folder. And within that folder, I have subfolders. Say the feature is, I don't know, Bluetooth device, whatever. And in that subfolder, I reference every commit by its SHA. It's a subfolder. And within that commit referencing folder, I create so-called feature fact files. These files describe how the feature and the commit belong to each other. Usually that's something like they are connected. So these files do not contain too much information yet. This graphic might be a little easier to understand. I have this metadata branch. This is a folder called feature 1. Then I have the subfolder called the commit ID, which I know will never change. That's like a fundamental of the Git concept. And then I can add whatever JSON file in this case to describe their relationship. I decided to have multiple JSON files because that allows me to never ever have merge conflicts. Whoever adds information to the feature commit relationship will create a new file. Because it's an add-only concept, I will never have a merge conflict, which is pretty nice because you do not want your users to have merge conflicts. The resulting Git structure would look something like this. This is your usual Git graph. I just have multiple branches. They touch files. Each of the circles is a commit. The blue one is the metadata branch. It is an unrelated branch, so it doesn't share any commits with the main branch. Other than that, it's just a regular branch. You can push to that branch, you can pull from it and share information that way. I don't really care about the order of the commits because whether one commit was done before another doesn't really do anything for the folder structure. As you can see, I can replace the concept of feature with whatever I want, right? And that information would still be persistent. Also, nobody requires me to add these information while creating the commit. I can add this information later on. For example, as a more experienced developer, I can help more junior members to actually create the corresponding files, and they do not need to do that and still can work. I'm not even required to all the time do that concept. I can say, oh yeah, I now want to add information, and for the next couple of weeks, I'm not doing that, and then I later will resume to use that concept. How do I get users to actually use command line tools to help add or retrieve information from that concept? Git has a super interesting concept which revolves around, you write a script, you name it git dash whatever you want to call it, you save it somewhere in your path to make it executable, and now you can use it just like another git command. You might have known that, you might not have known that. That's super easy, especially if you're using Python, because Python has an ecosystem that allows you to pretty easily install scripts as well. Even if you're not interested in the feature metadata concept, adding such extra subcommands might be very nice for depending on the project that you're working on for generating additional information and adding them to certain structures in your company. So how did I combine this everything? I already mentioned I wrote a Python-based tool. This is the QR code to the actual GitHub repository. It has installation information. It still does have bugs, so do not fully rely on it, but if you want to test it out, you're more than welcome to do so. Then I researched the commands that I wanted to do, then I created the metadata branch, and then I could do a user story. During implementation, I came up with some interesting concepts of Git that I wanted to share with you as well. Because adding feature information equals committing to another branch. And as you might or might not know, you cannot easily commit to the branch that is not currently checked out. So how do I add information without needing to have a clean workspace? There's a cool tool called Git Fast Import. It's a backend to import data into Git. And why am I sharing this? This is the interface that you use when you're switching from whatever system you had prior to actually using Git. It was built to convert from, I think, Subversion or something. Yeah, Subversion it was. To just keep your history and turn it into Git. So if that's interesting for somebody, Fast Import is your friend. Another thing was, how do I access information of that branch during development? And because Git was intended to be a file system, there's the command lstree, which allows me to query another branch, just like I would query another folder. I'm not sure if that is important for anybody, but I found that a super nice hack. Yeah, so I used a ton of Git concepts to build my prototype. I also did a user study. So if you're actually interested in how the tool works, I guided you to the form. It is meant to be an asynchronous test. So it guides you through the process of setting up and comparing the current tool to what I called traditional Git. It uses the format of conventional commits, which is a developer discipline resource of how you can ensure that everybody can read your Git messages well. I also added some information about the user preferences. As you can see, people on this side would rather prefer traditional Git, most of them because they already used it for a couple of decades. And these are the people that prefer the new tool. It still has some work to do to actually be usable, but I hope that the concepts help people to reason about additions in their workflow that they probably not deemed implementable. But now that I've seen this, it's interesting. Yeah. Cool and useful stuff about Git. First and foremost, whatever you commit, you shall not lose. This is the second part of my talk where you hopefully can take home some interesting commands. It's 2 years at this point. I just randomly deleted 3 weeks worth of work because I rebased poorly. I just kept the stuff that I didn't want to keep, and everything else was too big to be kept in the cache of my Windows-based computer. And I know that I am in the wrong for using that, but never mind. I deleted 3 weeks worth of work, and I was stressed to say the least. And I actually found out that work was not actually lost. I just didn't know how to access it. Git only deletes your commits after 2 weeks. So Git has a garbage collection system, and whatever commit you create is usually referenceable as being part of the history of a branch or being a tag. If a commit is neither, it can be deleted by Git. But it's only done after 2 weeks. What you can do is use a command called git reflog, and I also input the output. Can you read that? Yes. So what you can see here is the history of how my current head has changed. So if you, for example, do a rebase or merge and you do something wrong, you would see that somewhere along these head outputs, I could see the head prior to me really messing up. And you can always do git reset your commit, and then you're back to that state of work. So whatever you commit, you do not lose. I hope that helps with making more commits and making them more reasonable. Also, not all commits are part of a branch. You can actually get into the so-called detached head state. You do git checkout and then a tag. You can do changes on that state, create a commit, and tag that commit. That is super reasonable if you, for example, notice that you have put in the wrong link for your supplier, for example. You might not want to have these additional information somewhere else in your project. Not all commits need to be part of your branch. You can update tags. You can create commits, retag them, merge them somewhere else, cherry pick them, whatever. I actually used that to do some hot fixes in software releases that I messed up. Maybe that's something that you find interesting as well, so that you can do releases that are outside of your usual branch history of Git. You might not like that, then don't do that. It's possible. Navigating the log. The log command allows you to do tons of regex, tons of diffs. You can go between different tags. So if you do git log and then 2 tags, it shows you all the commits that are happening between those tags. Just a shout out to do some research if you find yourself knowing that there is information in the log, but you don't know how to access that. If you massage the current LLMs, they will help you with that. You can set up merge and diff tools to your liking. Tool help is the command that shows you the list of what you can set up. There are visual diff tools, which is increasingly important when you're creating visuals of your PCBs, for example. You could also write your own tools. That is definitely more challenging, but you can customize a lot of Git tools to be working with certain files that are not code related. Git worktree. If you want to work on multiple branches simultaneously without having to do git clone new folder name, you just do git worktree, add your new branch, and then you have multiple folders in your computer and can work on them separately. I have switched to only using git worktree. Love that a ton. And I'm speeding it up a little bit because I'm over time, I think. Something else is Git nodes, which I found super helpful to retroactively add information to commits without altering them. Usually, if you edit your commit message, you create a new commit because the message is part of the SHA, right? But if you do a Git nodes add, then you select your commit. I chose a tag for better readability, but you can put in whatever. You can just add a message and it will appear in your Git log. You can see where it says notes, even though I added that long after creating that commit. Super helpful if you know that a certain commit has an issue that you want to track in your history. There are people that say Git nodes are hard to sync. I have not that much experience with it. Just bear that in mind, because the argument is apparently that nodes can be increasingly cluttered if you add multiple ones. Speaking of adding information in your Git message itself, there's the concept of trailers. Some of you might have used co-authored by from GitHub. What's a trailer? It's a part of your commit message with a certain format being key, the thing with the 2 points, colon, value. And this is parsable by Git. Feature tools like Jira, I think, use that to reference the issue that a certain commit belongs to. You can add the information either by manually typing it out or using the trailer variant, and then it's a key value, and you can add however many you want, and they'll occur in your Git log as well. Is this the end? Kind of, and then also kind of not. I think Git shows that there are tons of workflow refinements possible with the tools that it brings. You need to know about them to decide which ones are helpful for you, which ones are easy to use, and which ones you're like, no, that's not for me. I personally find it super nice to see that storing meta information in Git is actually not too challenging. So I'm currently in the process of figuring out which meta information might bring the most actual benefit to industry. If you have a use case in mind, please contact me, because I'm thinking about doing some research projects and not later on. Yeah, if you want to contact me, my social media handle is Tabea the Unicorn on most of the platforms. I'm currently a software engineer at Auto-Intern when I'm not doing conferences with the Skunk Force nonprofit organization. I have strayed from the honorable path and started doing front-end work with Angular. I'm doing Python, and I'm still interested in tons of sensor projects because I really like having industry applications where I can see something being built. So yeah, that wraps it up. I hope you learned something and want to discuss ideas of adding meta information in Git in a couple of minutes.
Hello, thank you for your presentation. I have got a question concerning KiCad and Git. The problem I think about is if I have a finished PCB, I would like to have the code as a QR code or something like that on the PCB which reference to the Git version. The problem is if I check it in, I got a code or number, but I get the number after I check it in. So to put it on the board, I would have to recheck it in.
I had a similar problem by creating language files for my front end because I have a finished release and then I still need to do the translation. What I found out is I tag something as releasable, and based on that commit, I do another commit out of every branch. So that's the commits cannot be part of branches kind of state, right? Let me go back to that. So I would check out the releasable tag, make all the alterations that I need to do for the actual release, make the commit, and write tag dash whatever actually releasable. So that the work of, well, that's work that you don't want to keep in your project, right? So does it make sense what I'm explaining? How can I explain that? So let's say you tagged your version, right? So you know you're ready to release. You get from that tag, you get your information that you want to put on the board. You do git check out that tag. So you're not part of a branch anymore. You do the work, whatever you need to do for creating that information for your PCB silk screen, I guess, right? You commit that work, and then you do git tag means dash actually finished, whatever, and then you can push that tag, but that commit will not be part of your history. And you know that the actually manufactured version of the PCB is the one that says dash actually producible. Does that make sense? So you have like a 2-tag system. You decide that every tag has to have a tag named dash releasable version. I found that worked quite well. So language files are similar because I need to alter them at the end. And I have come up with that system and I'm pretty happy with it, even though it sounds a little strange at the beginning. I can show you later on if you're interested.
Yeah, so first off, a comment, gitref log, very helpful. And actually, you don't even need to invoke gitref log because you can reference all the historical options by just saying at curly brace number curly brace. And you can combine it with the caret and tilde notation. So like you can say git show at curly brace 2 curly brace caret 3, and that would be the third like direct parent of where you were 2 checkouts ago. Anyways, but my question is, you created this whole separate tree and separate object types. So was there any sort of information that could not be effectively stored in commits, commit message body, trailers, Git nodes, Git branch descriptions, tag messages, and so on?
Well, yes and no. So if you were the perfect programmer, you would probably input this information correctly all the time. If you retroact, so sometimes these feature models kind of change their structure for whatever planning reason. And then your features might have different names, for example. Then you theoretically would need to change all the Git messages, which would mean rebasing because you'd alter the commits, right? So saying the commit itself touches the code, and then I associate the meta information makes that easier because it's easier to change retroactively. But in theory, you're right, this concept would not be needed if we knew about a static feature system and we could just input it into the commit message itself. The other point is programmer's discipline. If I do not format that correctly in the commit message, that information would be lost as well. You have a second question.
or either in the context of your work or your exercise, or really have
Some information that you wanted to change post commit, but you still wanted to like version control it.
So you want me to give an example of adding information post commit, right? Like an example for it, just to understand your question correctly. Specifically, an example that I actually had was I marked a version of my code as fixes bug XYZ and described how. And then I realized that I did not execute the tests correctly, so the commit was wrong. And I already worked on top of it, so I only realized a couple of commits afterwards, so I needed to tag it as non-working. I could theoretically use nodes or the metadata system. What's your preference? Really depends on what works for you. I do see that this is not a common use case for every developer. Like it's a very specific subset of people that work within the realm of features that are way more intrigued of discussing where do they exist, how do we plan them, that kind of stuff.
I was not sure if I actually wanted to get into the topic, but I really wonder for these use cases where we actually create outputs out from code, basically from original source data, we create generated data. Git is ubiquitous. It feels like almost like monoculture. First question, have you ever looked into that? Like what alternatives exist at this point? And second thing, maybe it's time for a version control system which also supports the definition of transformations. So you have code, then you generate something from it, and what is generated is a first class item as well. Like same version but different state, basically, if you get what I mean.
So if I caught you correctly acoustically, first question would be, what are other software that solve similar problem, right? The second, yes?
Like basically just I wanted to say alternatives to Git. I think it's an interesting topic. I wonder if you looked into that.
Do I off the top recall? I know there are some research prototypes that evolve around that topic because my professor works in that realm as well. I am not aware of anything that's actually used widely in industry. Regarding your second point, which is about should transformations of code also be first-class citizens in version control? If they are too large, you cannot commit them. So GitHub, for example, refuses anything above 1 gig or 2 gig, I think. So that makes it hard. Also, in my opinion, I want to only commit stuff that I am responsible for. The auto-generated stuff would not be it. That being said, I do agree that extending Git to fit version control problems like hardware-related ones that are not just tags that you manage, but rather more files with more information, extending Git definitely makes sense and even building on top of it. Any other questions? No? All right. Thank you so much.